Let's do a problem on work. Assume that we have a tank. The tank is in the shape of an inverted cone. That cone has a height of 10 and a base radius of 4. We'll assume that the tank is filled with water up to 3 feet from the top of the tank, and that what we want to do is pump the water out of the tank until the tank is empty. Question is, how much work is required to empty the tank? All right, so let's draw some pictures. Start with the inverted cone. Bring in the radius. For reference, bring in the axis of rotation. Next, denote the height of the cone, 10. And then the water. The water is 3 feet from the top of the cone. Then off to the side, make a nice little legend. What we'll do is we'll say that we have the top corresponding with 0, and then the bottom of the cone corresponding with 10, so that water only occurs between a depth of 3 up to a depth of 10. Now, add an arbitrary depth into the water, let's say a depth of x. Draw the cross-section of the cone. Fill in that cross-section, you'll have a disk. Okay, so that's our picture. And what we'll do now is we'll think about A of x as being the area of this disk. And we can set up our work integral. Our work integral, we're letting rho denote the weight density of the water. That the work integral is the weight density times the integral for where the water resides, depth of 3 up to a depth of 10, with integrand the distance times the area of the horizontal cross-section. So in this setup, distance is representing how far we need to transport a horizontal cross-section. So that this dark blue disk needs to be transported up to the top, and that is simply a distance of x. So we can swap out our distance with x, and thus with the work integral already set up, we have reduced our problem down to simply finding A of x, the area of the cross-section. To find that area, we're going to use similar triangles. We want to draw these two similar triangles. The red triangle, the larger triangle, corresponds with the cone. And as such, we can label the red triangle with measurements 4 and 10. The smaller right triangle corresponds with the disk. And then that disk is at a depth of x. If we vary that x, then we're going to vary the height of the right triangle as well as the radius of the right triangle. Well, the height of the right triangle, since x is measuring the depth from the top, then looking at x, how far is it from the bottom? That would be 10 minus x. So h of x is 10 minus x. Good. Now let's use the fact that in similar triangles, we can take the ratio of the base over the height, and set it equal to the same ratio, the base over the height of a similar triangle. And that in this equation, what we're interested in is the radius. So we solve for r of x. And again, our objective was to find the area function at a cross-section taken at a depth of x, and we have done so since we've come up with a formula for r of x. Now, armed with this a of x, we can go back to our work integral. Here's the work integral. We've come up with a of x, so we now plug in. We get this integrand. We'll need to distribute the x. And then after distributing the x, we have elementary integrals, which we can evaluate to find antiderivatives. And then plugging in the bounds, a little bit of a computation there, we come up with a value. And this is the work required to empty the given tank. Excellent.